We study 16, fluid statics. Find the first statement regarding the units of pressure. ATM is the standard unit for atmospheric pressure. It is relative to the pressure at the sea level. It is the average pressure at the sea level. And Torr is named after Torricelli, who studied the mercury column. It is equivalent, 1 ATM is equivalent to 760 millimeter height of mercury column. And it is not 1 Torr, it is a 760 Torr, that is equivalent to 1 ATM. PSI is usually used for the tire pressure, and that is pound per square inch. PSI, pound per square inch. Pascal is the SI unit for the pressure, Newton per meter square. And if you multiply meter, both numerator and denominator, it becomes joule. Joule per cubic meter is also Pascal. Rho V square, if you look at this, joule is for the energy. You remember 1/2 mv squared. That is the energy, kinetic energy. For example, mv squared divided by volume. Mass per volume is density. Multiply velocity squared. Aha. Rho V squared is equivalent to the pressure. Rho V squared, density, mass per volume, multiplied by velocity squared, rho V squared, is of dimensions of pressure. If you look right in terms of mass, length, and time, then you will find this. I already explained this. Number 3, find the false statement regarding the pressure inside the liquid in equilibrium. Pressure in a liquid is determined by atmospheric pressure outside and the depth of the liquid. But detailed expressions will be found in later. And let us consider the pressure on the boundary. The pressure inside the liquid has no direction. That means just like a tension on a string, it is either to the right, to the left, depending on the object the force is applied to. For example, in a container, pressure of the liquid is toward the boundary outside. And this is the pressure. And pressure is force divided by area. And if I choose a very small amount of area, then we have the sigma vector. That the sigma is the area multiplied by the unit normal vector to the surface. Therefore, the force applied to this patch, small patch of the container, is the pressure multiplied by the area vector. Area vector has the dependence on the area itself, and it is a vector, so it is parallel to the unit vector, normal to the surface. Because liquid does not exert the force tangent to its boundary surface. It is because ideal liquid does not have any reaction to the shear force. That means the strain of the shear stress is infinite. That is quite important. The direction of the force is always perpendicular to the differential surface element. Orientation of the force is from the liquid to the other side of the surface. For example, inside a container, pressure of liquid is toward every direction, and that are in equilibrium. But if it is at the end of the surface, then it's acting on the normal to the surface. Px is independent of the coordinates of the horizontal plane. It is because it under, just like a springboard, there is a shear stress, then there is a finite strain, delta L, and this is L. Strain is a deformation divided by the whole length. And this strain is finite for a springboard or any solid object. However, in liquid, it cannot sustain any force that is tangent to the surface. That means if there is any force, the liquid, form of liquid changes on shape. Just like depending on the various shape of container, if you pour water, it fills the container completely and the surface is flat. That is because of this reason. Number 4, first statement regarding the ideal incompressible fluid. Incompressible. For example, gas is compressible. Gas is not an ideal fluid in the sense that it is incompressible. Whatever pressure is additionally applied, the change in the pressure at a point is the same everywhere inside the liquid. This is Pascal's principle. Pascal's principle. If there is a container and there is an incompressible liquid, if you initially there is a atmospheric pressure, for example, from outside, and if I add additional pressure, then this delta P is immediately transferred to everywhere, including the other side, the other end. That is Pascal's principle. If we add a drop in the liquid, the drop spreads immediately to create a flat layer on top of the original liquid. There's a container, it is a liquid, a drop pours down, and immediately it becomes flat and make an equilibrium. If it is not an ideal fluid, for example, if it has a viscosity, then this drop will stand up on top of the flat surface of liquid. So it is not an ideal liquid in that case. Because the shear modulus is 0, shear modulus is 0 because the shear strain is infinite. Shear strain is delta L over L, and it cannot sustain any force. Because of that, it becomes infinite, and stress divided by strain is a modulus, and shear modulus, because denominator is infinite and stress is finite, it becomes a 0. So shear modulus of the ideal liquid is a 0. Because the compression modulus is infinite, compression modulus is if you press down a liquid, the pressure change delta P is transferred everywhere by delta P exact amount without delay. However, it is incompressible, so there is no change. There is no change. Delta X times the cross-sectional area delta V is a 0. If under any compressive stress, there is no strain in compression. So stress, finite stress of pressure divided by strain, because the strain is 0 for the compression stress, 0, finite, it is infinite. So because the compression modulus is infinite, impossible for points of different levels to have different densities. That's correct. This is a U-tube. A U-tube with an even cross-sectional area, actually it doesn't have to be the same. This cross-sectional area is independent, but as a simplest case, we consider the cross-sectional area is the same. Cross-sectional area A are the same everywhere. And we have external force applied by the atmospheric pressure. Sure, there should be some difference of the pressure due to the air. However, because the air density rho is very small. For example, the atmosphere, this is the Earth, and we have a big amount of air, and the densities are different. Anyway, this amount of air pressure, this amount of gravitational force due to the whole amount of air, this is the surface of the Earth, is equivalent to about 10 meter of water column, or 760 millimeter mercury column. They are all equivalent. Because this height is very tall, this slight difference in height doesn't matter at all to create any significant difference between the air pressure of these two places. So we ignore the difference between the two levels of the atmospheric pressure because the density is very small. However, the density of liquid in comparison with air, it is very large usually. Because of that, the gravitational force due to the weight of this liquid. Weight, how can I compute the weight? Rho, this is 2. Volume, cross-sectional area, and height, h2. This is mass. So mass times gravitational acceleration is necessary. And here, they are in equilibrium with the same height, the horizontal line. So this amount of weight should be equal to this amount of weight. And this amount of weight is rho, if I know the density, rho 1, A, H1. because of the same gravitational, the same cross-sectional area, we have, what we have is multiplied by gravitational acceleration, then they are equivalent. In addition, there is a external force, that is a pressure multiplied by the cross-sectional area is the force. They are the same. So we have the same amount of pressure due to the atmospheric pressure, and the additional pressure is given in here. And the common cross-sectional area has been cancelled already. This is the reason why the pressure inside the water is increasing as the depth increases. So if you dive into the water, you should be very slow. If you go down too fast, your ear will be broken. The pressure of the left tube and right tube are at the blue horizontal level. These pressures are the same, and actually the forces are the same. The weight of the blue liquid above the horizontal, oh, this is what we have already solved. And after canceling P0, and we can compare the density by measuring the height of the two columns. 6, again, we consider an incompressible ideal fluid. Pascal's principle is a consequence of the incompressible fluid. If it is compressible, if I press a piston, and this is the air, there is some time, some delay in time to get this applied force transferred to the right side. However, if this is incompressible, as soon as I press, this lost amount will immediately comes out on the other side. So incompressible fluid results in Pascal's principle that transmits the force from any point of liquid to any point inside the liquid, the same volume. The bulk modulus of incompressible fluid it has been repeatedly solved, so let me pass this. 7. Find the false statement regarding Pascal's principle is a consequence of incompressible fluid. Okay, bulk modulus of an, let me pass. It is the same problem. Now let us solve this problem. We remember, if I have atmospheric pressure P0, and if I have some point inside the liquid, the difference of the pressure here, there is tiny hole is on top of this spherical surface. So there is a condition that P0 is fixed at angle theta equals 0. If I want to know some pressure at some point inside the liquid, what I need to do is just measure the depth from the point where the pressure is fixed. We know the pressure here is P0, and this amount is the height, depth, rho g h. If I know this h, then answer is this. And what is h at point A? Just trivial. This is r, and this is r cosine theta. So this is h in this problem, and h is r 1 minus cosine theta. So the answer is this. You can just follow this to find out the definite integral. Definite integral, we have to evaluate definite integrals to find the exact value for the pressure inside the liquid. A spherical shell of radius, the same situation. There is a tiny hole in here. And what I would like to know is the net force of the liquid applied to the whole surface. We call that the sigma vector is the sigma, and hat is the unit normal vector of a patch. And the question asked you to compute the net amount of force. You remember the F applied to the sigma is the pressure at x point x, the sigma integrate over the surface. And how can I do that? The sigma is area of this patch. Area of this patch is, this is radius, and it's polar angle, and this amount, this is r, d theta. And we have azimuthal angle dependence, and this is a radius, r sine theta, and this amount is r sine theta d phi. So this sigma is r squared sine theta d phi, and theta runs from 0 to pi, and phi runs from 0 to 2 pi. And I told you we can always express in terms of r squared dc d phi, where c equals cosine theta. In that case, the integral of c runs from -1 to +1. And this integral is always simpler than the polar angle integral. Okay. The sigma at this point is parallel to the unit vector along the radial direction. We repeat it too many times. I don't explain how I get this. And the area is r squared d theta sine theta d phi. And we just have found that the pressure at this point is atmospheric pressure plus rho gr 1 minus cosine theta that we already obtained in this problem. And using this value, I can substitute these into df, r squared, and pressure is here, and unit normal vector is here. Now, it's better to replace this cosine theta as c. And you will find integral over angle theta, these. However, if you evaluate the phi integral, we have a cosine phi, whatever theta dependence there may be, because of this integral from 0 to 2 pi, sine phi, cosine phi, all of them are vanishing. It is a trivial integral. They are all zero. So even though the initial expression looks very complicated, what I have left is everything is gone. And what I really need to evaluate is just cosine, sine, and this integral. And in here, this one is to be replaced with the cosine theta. And if I rewrite this df is r squared p0 plus rho gr 1 minus c, and then E3 hat c dc. And the phi integral, here phi dependence doesn't appear. The phi integral is just a trivial integral to pi. So what I really have to do is integral c dc from -1 to 1. High school student can do this integral. And another integral is another trivial integral like this. If you can evaluate this, everything is well done. This is what I have written. And in here, the first term, the p0 term, we have c integral. And this is odd function from -1 to 1. Always vanish. And the other integral is 1 minus c. And if I expand this integrand, it is a c minus c squared. C is again vanishing because it is an odd function, and only the even function survives. And the answer is minus 2/3. If I substitute these values, this is vanishing and this is a minus 2/3. The answer is, remember, this 2 pi came from the azimuthal angle integral 2 pi. And we have density, and we remember volume of this sphere is this. And volume multiplied by density should be the mass inside the sphere. So, except for G, this is mg, and we have negative sign on it, and found this. Remember, the liquid has its own mass m. However, before evaluating this, we expect that because this mass m, it will apply the net force at the center of mass, something like mg. However, because it's a liquid, this lower part of the liquid and upper part of liquid, their force is always perpendicular to the boundary. And you will find that the force, this force and this force differ. But only if we integrate over the whole surface, you will get mg. In the next problem, you will find the difference of the two forces. The net force applied to the annular boundary patch in the region from C to C plus dC is this. We already have obtained this patch. Sum of this patch, the force applied to this patch is this one. Now, let us compute the force applied to the, let's see, we are integrating from 0 to 1. 0 to 1 means this is theta equals half a pi and cosine theta equals 0. This point theta equals 0, cosine theta is 1. So upper hemisphere here. What we need to evaluate is the xc integral 0 to 1, and the other one xc 1 minus xc dx 0 to 1. This integral is a known. And we know this is 1/2, and this integral is xc integral and xc square integral. That is a 1/2 minus 1/3 and 1/6. Therefore, we apply this one as an integral from 0 to 1 of xc. Then this 1/2 and 1/6 is to be substituted in the integral. And because we have 2 pi coming from the azimuthal angle integral and r squared as an over factor, here pi r squared 2 cancels, so p0 multiplied pi r squared, that is actually the cross-sectional area of a radius r. Atmospheric pressure is equivalent to give the total force P0 pi r squared, that is pressing down the upper hemisphere. To sustain that atmospheric pressure, the liquid applies the force equivalent to that one. The net force applied by the air to the liquid is downward. Because it is coming out of the liquid, it is opposite direction, and the amount is equal. So this contribution is to sustain the atmospheric pressure, and that is exactly the same as a P0A, something like that. And we have this one. We factor of 2 times 1/6 is 1/3, and we have a pi r squared and additional r, so pi r cubed. It is a 1/4 of the whole volume. And whole volume is this one, and the amount of mass is pi r cubed and rho. This is the total mass. Therefore, we have 1/4 of mg plus the equivalent force to sustain the atmospheric pressure is added. We have found this amount of 1/4 of mg is applied to upward. This liquid applies the force by this amount, and in addition, 1/4 of the whole amount of mass is going up. It's very important. Because of this, you expect the amount of force pressing down the lower hemisphere. That will be the whole mass of this mg, and in addition, we need 1/4 of mg is to be applied to the lower hemisphere. Okay, we can compute the same integral from -1 to 0, -1 to 0. This integral is a -1/2, and this is, you'll find this is -1 and 1/6. You remember what we already have found is this amount, and what we like to evaluate is another force that is applied to the lower hemispherical surface. Finally, the answer gives this amount. And if you add this one to previously obtained result that is applied to the upper hemisphere, that is plus 1/4 of mg. And if we add this one, you will find minus mg. Minus mg because E3 is upward, so net force is this amount. You can find the sign is opposite for the part that is for to sustain the atmospheric pressure is negative sign because in the case of upper hemisphere, atmospheric pressure is pressing down in here. However, in the lower hemisphere, atmospheric pressure is going up. You know, pressure is to everywhere. When we consider a boundary, at this boundary, atmospheric pressure is pressing down, and in here it's going up. So because of this, the sustaining force is not plus but minus. That is to make an equilibrium with the atmospheric pressure. And this part is not the amount of its own mass is bigger than its own mass. The reason is that it had to apply the force upward, defying gravity, because it is liquid. In order to cancel this amount, we need a bigger amount than its own weight mg. So container must be constructed stronger than to sustain its own mass. Very important. And this amount is depends on the shape of the container. You can see what's happening if we replace this one into a cubic container. Cube has all size L. Again, the density rho of liquid is filled in this liquid, in this container. And this part is open, and atmospheric pressure P0 is applied on the surface B. B accept the uniform air pressure P0. So what is the amount of force? P0 times area. What is the area? P0 times L squared. What is the direction? It's down the direction. That is minus E3 hat. Okay? So this is equilibrium. Outside applies this force, and B must sustain this force because this liquid in equilibrium. The answer is just to replace the sign with positive sign, P0 L squared. This is the force applied by the liquid to the air. This is the answer. Next, we consider surface C, just the bottom surface. Then the liquid here, its pressure is P0, but the depth is L. So we have P0 plus rho G depth. Depth is this. So P0 plus rho G L. And any place on this surface must have a equal amount of pressure. Therefore, this pressure, uniform pressure, will give the force, this amount, multiplied by area squared. And what is the direction? Direction is downward because the liquid is pressing down. So minus E3 hat is the direction that is downward. You will find in this case, a cubic case, this amount cancels. This one is exactly the same amount and opposite direction because air pressure is pressing down and down here air pressure is going up. So they cancel. Just like that, this one cancels this air pressure and the first term cancels that air pressure from downside. And then the net effect of the weight comes here. In here, it is mg. Instead of the previous case, we have 5/4 that is greater than mg in magnitude. So we have a different result depending on the shape of the container. Next, we consider the force applied to these four surfaces. Because of symmetry, we expect that amount of forces of these four sides will be the same, except for the direction. And because the pressure is the same at every level, every depth, it has a P0 plus rho Gz, and that Z varies from 0 to L. So we need to evaluate this integral. And first term is the same. It is just the area, P0 multiplied by area. And the other piece is due to the weight of this liquid, and this will give 1/2 factor in here. But direction of the forces are always normal to the surface. These two cancels and these two cancels, and net effect of the four sides, net force of the four sides cancel exactly. (13) We use the same problem. This is a repeated calculation, the same magnitude, but these two pairs, A and A prime, D and D prime, they cancel exactly. Okay, that's it for today.